Hello, this is Mr. White, and this video is on the product rule. Here are the two exercises that we're going to do in this video, as well as the times at which they occur. So let's jump right into the first exercise there. All right, we're asked to find w prime of x and w prime of c. And rather than elaborate on what the distinction is, if you're not clear on it, as a relatively new calculus student, you can be forgiven if it's not totally clear to you what the difference is between those two requests. But rather than jump into the distinction, let's just do the problem, and in the course of doing so, you'll see what the difference is. All right, let's remind ourselves what the product rule states. The product rule says that if you are deriving one function, or the product of one function times another function, which we'll call f of x and g of x, that you do not simply take f prime of x and multiply it times g prime of x. That's what our intuition might tell us to do, but that is absolutely not true. What we do instead is we multiply, or we add the product of f and g prime to the product of g and f prime. And I prefer to, this is the order in which most books will give it to you, but I prefer to do it in the opposite order here. And the commutative law of addition says I can swap the order and it doesn't really matter. Now, why do I insist on swapping the order? Well, when we get to the quotient rule, you'll understand a little better why I prefer to do it in this order. But I'll generally do g times f prime, the second times the derivative of the first, plus the first times the derivative of the second. So let's go ahead and do that. And I should actually point out, we have a choice here, by the way. We have a choice. We don't have to use the product rule on this, this problem. Since this is a polynomial times another polynomial, I could just distribute that out, right? So I have that choice. And in fact, we'll go ahead and do it that way too. We'll compare and contrast. And part of your job as a new calculus student is to try to observe and pick up some ideas on how you're going to be able to tell when you would rather do it one way versus the other. When you'd rather use the product rule versus when, if given the option, you can avoid using the product rule. All right, so let's go ahead and do that. W prime of x. If we're going to take the derivative, so we're going to launch right into the product rule, and we're going to do the second function, g of x. So that's just x squared minus 3, times the derivative of the first function, our f prime of x, right? So that's going to be times 3x squared minus 10x plus 0. Again, I just took the derivative of this, and I trust by this point you're getting comfortable with just applying those basic differentiation rules of power rule and constant multiple rule. And we're going to add that. We're going to add that to f of x, the first function, x cubed minus 5x squared plus 2 times g prime of x, the derivative of the second. And when I was just about to run out of room here on the board, I look at that function, I say, wow, its derivative is very simple. It's just 2x, right? 2x plus 0 if you prefer. So I just barely got it onto the board there. And at this point, we're done with the calculus. I just need to distribute that out. So we'll do a little bit of algebra here. I'm just going to first, outer, inner, and last, FOIL that. So that's going to give me 3x to the fourth minus 10x cubed minus 9x squared plus 30x. And again, that was our first product there, 30x. Plus, let's distribute that second one too. Just distribute the 2x to those three terms. And I will get 2x to the fourth minus 10x cubed plus 4x. Okay? Now that I've distributed out, let me clear myself a little bit of room here. Now that I've distributed out, I can combine like terms, and I strongly suggest you come up with a system of keeping track of terms when you're combining them, if you don't have one already. So, for example, if I'm looking for my fourth degree terms, I like to circle them. So there's 5x to the fourth right there. Now I'll look for third degree terms, minus 10x cubed minus 10x cubed gives me minus 20x cubed. I've only got one quadratic term, minus 9x squared. And then the two linear terms, 30x and 4x gives me plus 34x. And guess what? That is our w prime of x. So notice that w prime of x is a function of x in its own right. And I can plug in any x value here that is in the domain of this original w of x function. This w prime will give me the slope at any point along the original curve. Now, what's the difference between that and w prime of c? Well, w prime of c is asking us to evaluate the derivative at this specific x value. So when x is 2, or as we say here, c equals 2, we'll go ahead and figure out what this slope is. So let me extend the page just a little bit here. And I'll simply just plug in that c value of 2. And that's going to be 5 times 2 to the 4th, minus 20 times 2 to the 3rd, minus 9 times 2 squared, plus 34 times 2. I'm going to intend to check this on a calculator in a moment, so I'd say let's use this as an opportunity to practice our mental math. And I suggest you do the same. 5 times 2 to the 4th, that's 5 times 16, that's 80. Minus 20 times 2 cubed. 20 times 8 is 160. So I've got 80 minus 160. That's negative 80 so far. Minus 9 times 2 squared. That's minus 36. So negative 80 minus 36 is negative 116. Plus 34 times 2. That's going to be plus 68. And that should give us negative 48. And if you're not totally comfortable with your mental math, I don't blame you, I understand, but at the same time, we're going to check with the calculator in just a moment anyway, so why not take the opportunity to practice your mental math? Okay, so in addition to checking with the calculator, I just want to really emphasize what it is that we've done here. What does it mean to say w prime of x equals this and w prime of 2 equals negative 48? Well, let's bring the calculator up. And I've just entered in the original function. And I'm not going to bother graphing the derivative. I'm just going to graph the original. And I've got some window settings right here that may look a little bit arbitrary to you, but they give me something that gives me a pretty good sense of what this graph looks like. So w prime of x would give me the slope at any point along the way here. W prime of 2, I'm expecting it to be negative 48. So let's see if that works. So second, calc dy over dx, I'm just going to press number 6 on the keypad. And I'm going to type in 2, that's the c value or the x value that we're told to use. And we get negative 48. And I figure that's a pretty good check. I can be pretty confident that the chances that I would get negative 48 on the calculator if I had made a mistake in all this algebra are pretty low. So I think that's a pretty good affirmation that we've done things correctly. And again, I'll just remind you that that means that the slope here at this point, the slope of that tangent line is negative 48. And if I wanted to find the slope of any of these other tangent lines at these other c or x values, I would plug in the appropriate x value here. So what I'd like to do right now real quickly, I'm not insisting that you do this on your homework for all problems, but it's not a bad idea to once in a while when you're learning a new rule, just prove that it's consistent with your prior knowledge. So we just did this derivative with the product rule. Let's now do it without the product rule and just compare and contrast. And again, get an idea for yourself as to try to develop a sense of when the product rule is the way to go versus not. All right, so if I'm not going to use the product rule, I just need to distribute that out. And if you haven't seen this before or I haven't shown you before, my favorite way of distributing out polynomials is to write a grid here, draw a grid. And in this case, I've got 1, 2, 3 terms times another 2 terms. So based on that, I'm going to make 3 columns and 2 rows. And if you'd done 3 rows instead of in 2 columns, that would have been fine too. But I'm going to put x cubed minus 5x squared plus 2 on the column headers, and then I'll put the x squared minus 3 along the rows. And I'll just put in each of those boxes, I'll put the product of the row and column header. So x squared times x cubed will give me x to the 5th. And then negative 3 times x cubed will give me negative 3x cubed, and so on. So here I'll put negative 5x to the 4th, 15x squared, 2x squared, and then minus 6. And I just add up each of those, I add up all the boxes, and I look out for like terms. So notice that here I've got x to the 5th, and I've got x to the 4th here, minus 5x to the 4th. And then I've got a minus 3x cubed, 15x squared and 2x squared will give me 30, I'm sorry, not 30, 17, I'm thinking ahead a little bit here, 17x squared, and then minus 6. Okay, again, that was no calculus, that was just algebra right there. So that's still w of x. And now we'll do some calculus. Now we'll take w prime, and we'll apply our product rule, 5x to the 4th. I'm sorry, our power rule, 5x to the 4th. And then here we'll have 20x cubed minus 9x squared plus 34x. And then the last one, we don't have the derivative of minus 6 would just be 0. And if I want to compare that to what we got when we used the product rule, notice I've got 5, negative 20, negative 9, 34. 5, negative 20, negative 9, 34. It's the same thing. It's the same w prime. All right, so again, what did you like better? Did you like the product rule, or did you prefer just distributing out and deriving? It really is your choice in this case. But let's go on to the next exercise where we don't really have a choice. Okay, these are not polynomials that we're multiplying here. These are both functions of theta, and we're simply asked to use the product rule to differentiate this function. So I've got one function of theta times another function of theta, but they're not polynomials. There's really no foiling involved here. So I have no choice but to use the product rule. So let's jump right in with that. J prime of theta. And again, I really need you to write that that's what you're doing. Don't just write the derivative underneath without saying what you're doing. So J prime of theta. And let's try to just apply the product rule without writing the rule down first. We'll do the second function, cosine of theta, times the derivative of the first. And again, I'm going to conceptualize this. I'm going to think of this in my head as theta to the 1/3 power. And I'll just apply the power rule and get 1/3 times theta. And then remember how we take that 1/3 up top and we subtract a 1? So that's like 1/3 minus 3/3. That's why I'm going to write negative 2/3 up here. Plus the first times the derivative of the second. So for the first one, I'll just put theta to the 1/3. And I would prefer to write it with the rational exponent instead of the radical. So I would prefer to write theta to the 1/3 rather than the cube root of theta, times the derivative of the second. So times cosine of theta. I'm sorry, times the derivative of cosine of theta. And that's negative sine theta. Okay, if you wanted to stop right here, again, I'm kind of flexible on that for short answers. On the AP exam, if you stop right there, you can still get full credit. But very often in the back of a textbook, you're going to see something that doesn't really look like this. You're going to see some further simplification. So let's go ahead and go a little bit further. This would be, if we wanted to try to simplify this in some way, we might say, okay, I've got a fraction here, and there's a 3 in the denominator. And in the numerator, I've got cosine of theta. And also notice that really that theta to the negative 2/3 power, that's the same as having a theta to the positive 2/3 in the denominator. And again, a lot of textbooks will say formally we really shouldn't have negative exponents according to many textbooks, although again, it's not my biggest battle to fight as far as I'm concerned. Okay, plus theta to the 1/3 times negative sine of theta. So let's put a theta to the 1/3 times a negative sine of theta. And in fact, let's go ahead and just make this minus. And that in itself is not a fraction right off the bat, but if for some reason we felt compelled to combine these two terms, I would need to do common denominators. So that's what I'm going to do. Now, why would we feel compelled to do that? I'm going to save that for another day, but I will simply say at this point that there are times where you really want to combine multiple terms into a single term. So let's do that by doing a common denominator. And let's do 3 theta to the 2/3, 3 theta to the 2/3. And again, in class we'll discuss why is that advantageous to do that. Okay, so now I've got a common denominator, 3 theta to the 2/3, 3 theta to the 2/3. And my numerator is simply going to be cosine of theta minus, and here let's combine. 3 theta to the 2/3 times theta to the 1/3 is going to give me just 3 theta. Pause if you need to, convince yourself of that. But that's just going to be 3 theta times, of course, that sine of theta there. And that is all over still 3 theta to the 2/3 power. And that is what many books would consider to be fully simplified. Again, even though I don't insist on it all the time, I would say that when you're checking the back of the book and you're trying to reconcile your answer with the book's answer, sometimes we need to go that extra mile. So we could definitely check this in the way that we've checked derivatives before. I'm not going to take the time to do that in this video. What I will do is simply say, let's imagine that we were to graph the derivative, the original function and its derivative. So rather than go through the full checking process, I just want to point something out. And if we've done it in class, I'll emphasize this. If we haven't done it in class, I'll introduce you to this idea that this here is j of theta, and the bottom graph represents j prime of theta. And I want to point something out to you if you're not already aware of it. Let's ignore the j prime for just a second, and let's look at the intervals on which j of theta is increasing or decreasing. So notice that j of theta is increasing all the way up to right about there. And that's where it reaches a maximum, and then it starts to decrease to right about that point there. And then it increases again all the way up to here, and then it decreases all the way down to here. So notice those increasing, decreasing intervals, and we've done that, and you may recall that from pre-calc. I hope you recall that. Increasing, decreasing, increasing, decreasing, increasing. And think of what that means from a calculus point of view. Think of what we'd expect for the derivatives. Wouldn't we expect the derivative to be positive here during the increasing sections? And wouldn't the derivative be negative for the decreasing sections, the downhill sections? Well, let's take a look at the derivative graph. And notice that if I were to extend these lines here, notice that's exactly what happens. So notice that on the derivative graph, I'm looking at whether the graph is above or below the x-axis. So again, we said that during an increasing portion of the graph that the slope would be positive, the derivative would be positive. And notice that the derivative curve is above the x-axis here. For this other increasing section, the derivative curve is above the x-axis. And that's really an asymptote there. And increasing above the x-axis. During the decreasing intervals, notice that the derivative is below the x-axis. So think about that. Think of why that makes sense. And this is just a further affirmation too. If you were to graph the function and its derivative curve, and if you were to observe that correlation, you could be pretty confident that you've done everything correctly.